Hello, and welcome to this presentation on complex numbers, specifically looking at the polar form, z equals to r angle theta. This presentation does assume we've seen a previous presentation related to the Cartesian form of complex numbers, and we will be converting from polar to Cartesian and then Cartesian to polar within this presentation. This presentation does assume you're familiar with Pythagoras' theorem, with basic trigonometry, sine, cos and tan functions, and also have awareness of compound angle formulae. A brief overview of the complex number presentation here. We're going to look at conversion from Cartesian form to polar form, and then conversion from polar form to Cartesian form. We need to be very proficient with converting from one form to the other. Then we're going to look at multiplication and division in polar form, which is much easier, you'll see, than in Cartesian form. But it's very important to recognise, as will be highlighted later, that you cannot add or subtract in polar form. The bibliography is shown at the end on which this presentation was based, and I would strongly encourage you to refer to this reference material for further information. The polar form of a complex number. If z denotes a complex number, and it's represented by a phasor shown in the diagram in figure 5, O to P, so this is the phasor representing a complex number, then in Cartesian form, also called rectangular form, the complex number can be stated as z equals to x, the dimension on the real axis, plus jy, the dimension on the vertical axis, the imaginary axis. Alternatively, we could express same complex number z in what's termed polar form, where z is equal to r associated with the angle theta measured anticlockwise from the horizontal real axis. This is known as the polar form of a complex number. Given that z is equal to r angle theta, the polar form of a complex number, r, which is the length of the phasor on the argand diagram, is termed the modulus or magnitude of the complex number z, sometimes denoted as mod z or simply z between two vertical parallel lines, indicating magnitude. To calculate the value of r, we use Pythagoras' theorem. So if we know the x, the value on the real axis, and the y, the value on the imaginary j-axis, we can work out the value of r simply using Pythagoras' theorem, which says the square root of x squared plus y squared is equal to r. The angle theta, which is shown here on the argand diagram, is measured positive from the real axis in an anti-clockwise direction, and it's essential we use that notation in our calculations. Theta is sometimes called the argument or the amplitude of z, and can be written as arg z for short. We find theta from basic trigonometry, so for the diagram on the left hand side here, theta would be the arctan, that's the inverse tan, of y, the vertical dimension from the j-axis, divided by x, the horizontal dimension on the x-axis. Note that arctan, y divided by x, is equivalent to tan to the minus 1 of y divided by x. We do need to be careful, as you'll see in later examples, using the tan function shown above does not always give the angle of theta, so we need to be careful on which quadrant the phasor lies within the four quadrants of 0 to 360 degrees. We'll look at that problem later on. Conversion from polar form to Cartesian form. From the right-angled triangle, labelled PMO in a diagram on the right, complex number z in Cartesian form will be written as x on the horizontal real axis plus jy on the vertical, the imaginary axis. From basic trigonometry, and reviewing the figure on the right, we can see that z is equal to r cos theta, and that would be this dimension across here on the horizontal real axis, plus jr sine theta, r sine theta being the vertical dimension here in terms of the vertical axis. So that's r sine theta. And simply factorising on that, we could write that as r outside of a bracket and cos theta plus j sin theta inside the bracket. I would suggest you take a moment to stop the video and think through how we found the r cos theta and the j r sin theta, noting that cos theta is equal to the adjacent side over the hypotenuse, so cos theta is x over r, and then rearranging for x we get r cos theta, and likewise sin theta is defined as the opposite side divided by the hypotenuse, so that will be sin theta is equal to y divided by r, and again transposing for y we get r sin theta. An important note is that whenever you're changing from Cartesian to polar form or vice versa, a sketch is very useful to help determine in which quadrant the complex number actually occurs. Students often make mistakes in working out angle theta because they don't realise that the phasor is actually not in the first quadrant, it's in, say, the third quadrant or the fourth quadrant. So they calculate using the tan theta formula an angle theta, but it's not the angle theta for their particular problem. So you do need to sketch the phasor, find which quadrant it's in before you actually know how to calculate angle theta. And we'll look at this in the examples that follow. Example 7. We're asked to determine the modulus in the argument, that's the r and the theta respectively, of the complex number 3 plus j4, and express this complex number in polar form. So if I sketch the complex number 3 plus j4, I've got 3 on the real axis and 4 on the imaginary j axis. To calculate the modulus r of the complex number, that's simply x squared plus y squared all square rooted. In this case, x is 3, so 3 squared plus y, which is 4 squared all square rooted, gives us a value of r is equal to 5. We can work out the argument, the angle theta, directly here because we can clearly see that the phasor of this complex number is in the first quadrant. So by using the tan equation, we're going to automatically calculate the angle theta. So angle theta, or argument, is equal to tan to the minus 1, the arctan, of y divided by x, that's the opposite divided by the adjacent sides. In this case, tan to the minus 1 of 4, the opposite side, divided by 3, the adjacent side, gives a value of theta equal to 53.13 degrees, or if you want it in terms of degrees and minutes, 53 degrees and 7 minutes. So the polar form of this complex number 3 plus j4 can be written as z equals to 5, argument 53 degrees and 7 minutes. Example 8. We're now asked to convert a complex number having a modulus of 9 and argument angle of 109 degrees into Cartesian form. So going the other way this time from example 7. So it's very important that we sketch our phasor in the appropriate quadrant. Now 109 degrees, don't forget we always measure the angle theta positive from the real axis in an anti-clockwise direction. It's absolutely essential you stick to that notation. When it says an argument of 109 degrees, that's the angle they're talking about. The length of the complex number, or the modulus, is given as r is equal to 9. So to convert from polar form, the r theta form, into the Cartesian form, the z equals x plus jy format, we use this formula. Z is equal to r cos theta plus jr sin theta. In this case, the r is 9, and the angle, or the argument, is 109 degrees, so we get 9 cos 109 degrees plus j, and that's 9 sine 109 degrees. So evaluating this expression on your calculator, and do make sure you're in degree mode, because the angle given in this question is in degrees, you should find you get a Cartesian complex number of z equals to negative 2.93 plus j 8.5095. So the negative 2.93 will be here, and the positive 8.5095 would be the value up here. And that defines our phasor and complex number. Exercise 5 has asked us to sketch the following Cartesian complex numbers and to convert them into polar form. So part 1, 3.5 plus j2, part 2, negative 12 plus j8, part 3, negative 6 minus j9.4, and part 4, 5 minus j12. I encourage you to sketch them first of all on the Argand diagram and then go through the process of converting them into polar form. The answers are given in the brackets here. The solutions are shown on the following slides. Exercise 5 solutions. We were given in part 1 the complex number 3.5 plus j2 in Cartesian form. I've sketched the complex number on the Argand diagram. We get 3.5 on the real axis and 2 on the imaginary axis, so our phasor for the complex number resides in the first quadrant. We've got to calculate the modulus r and the argument theta. Don't forget we measure positive thetas from the real axis in an anti-clockwise direction. So the modulus r is calculated using Pythagoras theorem, the x squared plus y squared all square rooted. In this particular case, the x, the real axis value is 3.5, so 3.5 squared plus the imaginary value of 2 squared all square rooted gives us a value of r equals to 4.03. We now need to calculate the argument, theta. We can clearly see that the phasor is in the first quadrant, so it's a direct solution using our inverse tan formula. So theta is equal to arctan, or tan to the minus 1, of the y divided by the x. In this case, that's arctan of 2, that's the j-axis value, divided by 3.5, that's the real axis value. From your calculators, that gives you an argument of 29.74 degrees, and it's been converted here into degrees, minutes and seconds. That's a button push on your calculator should you want to do that. Hence, in polar form, the Cartesian complex number of 3.5 plus j2 can be written as z is equal to 4.03 argument 29.74 degrees. Exercise 5, part 2, we're given a complex number negative 12 plus j8 in Cartesian form. Again, I strongly encourage you to sketch the vector on our Argand diagram. In this case, we've got negative 12 on the real axis and positive 8 on the imaginary axis, so the complex number resides here. So we need to calculate the value of r and also again theta. Don't forget theta is measured positive from the real axis in an anti-clockwise direction. So first of all, to calculate the modulus r, again we use Pythagoras theorem. So in this case, r is equal to 12 squared plus 8 squared all square rooted. So r is equal to 14.42. I'll let you check that on your calculators. Now begin to be careful here. We want to calculate the argument angle theta, but don't forget angle theta is measured from the real axis on the right hand side of the Argand diagram in an anti-clockwise direction. But if I use the arctan function here, I'm actually not calculating directly theta. If I use the arctan function, I'm actually going to calculate angle alpha. What I would do in this case is simply take angle alpha from 180 degrees, and that will give me angle theta. So in this case, alpha is arctan, or tan to the minus 1 of the y divided by x. So that's arctan of 8 divided by 12. And the calculator, that gives me an alpha value of 33.69 degrees. And the angle theta on the Argand diagram we measure from here in an anti-clockwise direction around to here. So in this case I can clearly see angle theta will be 180 degrees take away angle alpha. So in this case 180 degrees take away the 33.69, angle theta is 146.3 degrees. So here's an illustration how important it is to sketch the complex number on the Argand diagram initially, so you know exactly which quadrant the phasor resides, and then you know how to calculate angle theta. Exercise 5 continued, part 3. We're given the complex number negative 6 minus j9.4 in Cartesian form. We've got to convert that to polar form. So again, we've sketched the complex number on our Argand diagram. We have negative 6 on the real axis, negative 9.4 on the imaginary axis, so our complex number resides in the third quadrant in this particular case. To calculate the modulus r, it's simply Pythagoras theorem, so 6 squared plus 9.4 squared all square rooted gives a value of 11.15 for r. To calculate argument theta, in this case it will be 180 degrees plus alpha. We can clearly see that from the diagram. So to calculate alpha, that's tan to the minus 1 of y divided by x. In this case That's tan to the minus 1 of 9.4 divided by 6. That gives us a value of alpha of 57.4 degrees. So we can clearly see from the Argand diagram the angle theta. In this case we measured positive in this direction, so it means we need to add the 180 degrees to the 57.4 degrees to get angle theta, which is 237.4 degrees. So in polar form we can write the Cartesian complex number of negative 6 minus j9.4 as z equals to 11.15 argument 237.4 degrees. Or we could write the argument as negative 122.6 degrees, and that would be measured in this sense here. Exercise 5, part 4, we're given the complex number 5 minus j12, Cartesian form, and we're going to convert to polar form. First of all, we sketch the complex number on the Argand diagram, so that's 5 on the real axis this time, and negative 12 on the imaginary, so our complex number resides in the fourth quadrant in this particular case. To work out the modulus r, it's Pythagoras theorem, gives us 13 for the value of r. To work out argument theta in the positive sense, we'll need to calculate angle alpha. Angle alpha is shown here. So angle alpha will be, in this case, the tan to the minus 1 of 12 divided by 5. That gives an alpha value of 67.4 degrees. So to work out the angle of theta, we can clearly see from the Argand diagram that the positive theta value is 360 degrees minus 67.4 degrees. It gives us 292.6 degrees. And that would be the angle measured from here right the way around to here. That's positive angle theta. Alternative, we could actually calculate it as a negative value of theta, so we could actually simply state it as the angle of negative 67.4. So the alpha value in this particular case could be the theta value, but in a negative sense. So just bear that in mind. So the complex number 5 minus j12 in Cartesian form can be written in polar form as z is equal to 13, the modulus argument 292.6 degrees. Alternatively, you could write z is equal to 13 argument negative 67.4 degrees. That would give the same position. Exercise 6, we're asked to sketch the following polar complex numbers on an Argand diagram and convert them into Cartesian form. So part 1, we've got modulus of 2, argument of 30. Part 2, we've got modulus of 6, argument of negative 145 degrees. And part 3, modulus of 1.5, an argument of negative pi upon 3. So be careful, that third part is in radians. The answers of Cartesian form are given in the square brackets. I encourage you to stop the presentation before reviewing the solutions on the following slide. Exercise 6 solutions, part 1. We're given the polar form of a complex number of 2 argument 30. We sketch this on the Argand diagram. This would have a modulus of 2 at the argument of 30. Don't forget, positive 30 measured anti-clockwise from the real axis. We've got to convert this into Cartesian form. Don't forget that Cartesian form is z equals to x plus jy. From basic trigonometry, we've shown that z can be written as r cos theta plus jr sine theta. So in this case, for part 1, we've got the r value of 2, that's the modulus, and the argument theta is 30 degrees. So putting those values into the formula, we'll get 2 multiplied by the cos of 30 degrees plus j, and that'll be 2 multiplied by the sine of 30 degrees. And taking the arithmetic on that, we'll find that the complex number z is 1.732 plus 1j, or simply j. So on the horizontal axis, we've got the real number of 1.732, and on the vertical axis, we've got the value of 1 for j. Exercise 6 continued, part 2. We're given the polar form of a complex number here, 6 argument negative 145 degrees. So plotting that on the Argand diagram, the phasor length is 6 and the angle, it's negative 145 in this case, so that now will be measured from the horizontal in a clockwise direction to the phasor. There's our 145 degrees. So the phasor resides in the third quadrant. Again, noting Cartesian form, z is equal to x plus jy, and again we're using the basic trigonometry of z equals to r cos theta plus jr sin theta. So in part 2, the r is 6 and the angle theta is negative 145 degrees. So putting those values into the equation, we get z is equal to 6 multiplied cos of negative 145 plus j 6 sine of negative 145. Doing the arithmetic on that, we get z is equal to negative 4.915 minus j 3.44. So on the real axis we get the negative 4.915, and on the imaginary axis we get the negative 3.44. That's the Cartesian form of a complex number. Exercise 6 continued, part 3. We're given a polar form of a complex number, 1.5 argument negative pi upon 3. There's no degree symbol there, and the angle is in terms of pi, so that's obviously a value in terms of radians. So to get this complex number, the angle is negative pi upon 3. Don't forget, 0 to 2 pi is a complete revolution, so 0 to pi is 180 degrees, so pi upon 3 will actually be 60 degrees. This is negative pi upon 3, so the angle we measured from the horizontal in a clockwise direction, so negative pi upon 3 is really negative 60 degrees, and the length of the phasor, or the modulus of the complex number, is 1.5. So we've now got to work out the Cartesian form, that's the z equals to x plus jy form of this complex number, and again we're using the basic trig equation, z is equal to r cos theta plus jr sin theta. In part 3, the r is 1.5 and the theta, the argument, is negative pi upon 3. If you're using radians, don't forget to put your calculator in radians mode in this particular case. So z is equal to 1.5 multiplied by the cos of negative pi upon 3 plus the j 1.5 sine of negative pi upon 3. So if you calculate in radians mode, you'll find that z is equal to 0.75 minus j 1.3. So on the Argand diagram, we get on the real axis 0.75 and on the imaginary axis negative 1.3. That defines our complex number in Cartesian form. Questions 24 to 26 give us complex numbers in Cartesian form and wants us to calculate them in polar form, stating the modulus and the argument. So question 24, there's two complex numbers given here, parts A and B. The answers are given in the square brackets below. Question 25, again, two complex numbers given here, answers again given in the brackets below. Question 26, part A, has given us 2 plus j all squared to convert to the polar form. First thing you need to do is to square the brackets, so 2 plus j multiplied by 2 plus j, expand the bracket, collect the terms together before you undertake the conversion. And with part B, I would expand the bracket first of all and look out for your negative j values before you go into the conversion to polar form. Again, the answers are shown in square brackets below. Question 27 to 29, here again we've got Cartesian complex numbers to convert into polar form. Question 27, part A, complex number 6 plus j5, part B 3 minus j2, part C is negative 3 plus 0j in this particular case. All the answers are given in the square brackets. Question 28, part A, we're given negative 5 plus 1j, part B negative 4 minus j3, and part C negative j2. There's no real component there. Again, the answers are shown in the square brackets. And question 29, we've got negative 1 plus j all cubed. So again, be careful there, you need to expand the brackets first of all. Part B, we've got a negative j multiplied by the 1 minus j, so I'll expand the brackets there. Be careful of your negative j values. And part C, again, I would encourage you to expand the brackets first of all. Answers given in the square brackets below. In question 30 to 33, we're given polar form of complex numbers and we've got to convert them into the Cartesian form, x plus jy. For question 30, part A, here's your polar form, 6 argument 30 degrees, part B 4 argument 60 degrees, part C 3 argument 45 degrees. Answers are shown in square brackets. Question 31, part A, we've got 2 argument pi upon 2, B, 3 argument pi, and C, 5 argument 5 pi upon 6. So again, be careful there. Obviously the angles are in terms of radians. Answers again shown in square brackets. Question 32, part A, we've got 8 argument 150 degrees. Part B, we've got 4.2 argument negative 120 degrees. And part C, 3.6 argument negative 25 degrees. So just be careful with the negative theta values given there. Again, the solutions are in square brackets. Question 33, using an Argand diagram, we're asked to evaluate in polar form the following problems. So it's A, 2 argument 30 degrees plus 3 argument 40 degrees. Part B, 5.5 argument 120 degrees minus 2.5 argument negative 50 degrees. Answers are shown in the square brackets. As a hint for question 33, it says convert from polar form to Cartesian to add and subtract the numbers and then convert back to polar form for the final answer. So just be careful with question 33, a bit more work in there. We're now going to review multiplication and division operations using polar form. An important use of polar form as a complex number is that multiplication and division operations can be achieved much more easily than in Cartesian form. We're going to consider here a proof of multiplication in polar form. Assume we're given two complex numbers. The first, z1 is equal to r1 theta 1 and z2 is equal to r2 theta 2. If we're asked to multiply these complex numbers together to find z1, z2, then we would get r1 theta 1 multiplied by r2 theta 2. Now converting the polar form into Cartesian form, which we did on a previous slide, we could write that as r1 outside a bracket, then cos theta 1 plus j sine theta 1. That represents the r1 theta 1 for the first complex number. And then we multiply that by the second complex number of r2 and in brackets cos theta 2 plus j sine theta 2. So we've taken the polar forms for z1 and z2 and we put them into Cartesian form. All I've done on the next line is taken the r1 and r2 to the front of the equation because they're just a multiplication factor. What we need to do now is expand our brackets. These are binomial brackets, so we have to go through the standard expansion which you're used to. This is called the crab claw method. You may have your own method, but we're going to expand the brackets. So on the next line we get r1 multiplied by r2, followed by the expansion from the binomial brackets above. I'll let you review the expansion. What you need to be aware of course, is that during the expansion we get a j times a j. We've got the plus j sine theta 1 multiplied by the plus j sine theta 2, so we get the j squared sine theta 1 sine theta 2 term here. We know from previous work that j squared has a value of negative 1, so we replace that with negative 1 here. The final line here we've got r1, r2 outside of the big square bracket here, and inside we've got the binomial expansion accounting for the j squared, which is negative 1. Polar form multiplication division continued here. I've just repeated this line for convenience from the previous slide. Now if we refer to something called compound angle formulae, these are standard formula that's been proved in previous work, we could take the first expression in the brackets, the cos theta 1 multiplied by the cos theta 2 minus the sine theta 1 multiplied by the sine theta 2, and we could relate that to this compound angle formula. That's actually cos in brackets a plus b, where a plus b the angles theta 1 and theta 2 respectively. So what we have above is basically this format. We have the cos theta 1, the cos of a, multiplied by the cos theta 2, the cos of b, minus the sine of theta 1, the sine of a, multiplied by the sine of theta 2, sine of b. So I could rewrite that first term as simply cos of a plus b, but in this case cos of theta 1 plus theta 2. I can do a similar exercise for this part of the function, the sine theta 1 cos theta 2 plus cos theta 1 sine theta 2. That's actually of this format, sine a multiplied by cos b plus cos a multiplied by sine b, where again the a and the b are the theta 1 and theta 2 respectively. So I could now replace that part of the above function with sine a plus b, or using the notation in this question, sine of theta 1 plus theta 2 in brackets. If we now write that in terms of polar form, that would be r1, r2, which is the modulus, and then I would write the tan to the minus 1, or arctan, of the vertical component, so that's sine of theta 1 plus theta 2 in this case, divided by the horizontal component, that's cos theta 1 plus theta 2 in this particular case. We've now written it in terms of polar form. Now if we recall a previous trigonometric definition that sine theta upon cos theta is actually equal to tan theta, then in this particular case in the square bracket we can write sine of theta 1 plus theta 2 divided by cos of theta 1 plus theta 2 as tan of theta 1 plus theta 2, using that definition we've come across in previous work. Now notice in the equation we have tan to the minus 1 of tan of theta 1 plus theta 2 can simply be written as theta 1 plus theta 2. So in other words, they cancel each other out. So we end up with a final solution of the complex number z1 multiplied by z2 is actually written as r1 multiplied by r2, the moduli multiplied together, and then the arguments, the angles, added together. So to obtain the product of a complex number in polar form, we simply multiply the moduli together, multiply the r's together, and add the arguments, add the theta terms together. And this result is true for all complex numbers in polar form. So in comparison to undertaking multiplication in Cartesian form, when we have to use the expand brackets, collect like terms together, simplify, in polar form it's a much easier process. To undertake division in polar form, that can again be shown to be a very simple process compared to Cartesian form. With division in polar form, we simply divide the moduli and we subtract the arguments. So if we were dividing complex numbers z1, z2 on the previous slide, z1 divided by z2 would equal to the moduli divided, so r1 divided by r2, and the arguments are subtracted, so it's theta 1 take away theta 2. So when you compare the division in polar form from the equation in the bolded box to what we undertook in the previous presentation on division in Cartesian form, we have to find the complex conjugate of the denominator, expand top and bottom by the conjugate, collect like terms together and simplify. It's obviously much easier to divide in polar form. One very important aspect of complex numbers in polar form to note is that addition and subtraction in polar form is not possible. And that's a very important characteristic to be aware of. You cannot add and subtract in polar form. What you'll see in some of the following examples and questions is that they will give us an expression in polar form showing the two complex numbers added together, but you need to be aware you first have to put them into Cartesian form, add or subtract the complex numbers, and then go back into polar form for the final solution. So the questions will check us out to make sure we understand that we cannot add or subtract in polar form. That's very important for you to remember. Example 9. We're asked to evaluate the following three questions using polar form. Question 1. 8 argument 15 degrees to be multiplied by 4 argument 45 degrees. So solution of part 1, the 8 argument 15 degrees multiplied by 4 argument 45 degrees, we simply multiply the moduli together, so that's 8 multiplied by 4, and we add the arguments together, so that's 15 degrees plus 45 degrees. So the solution is 32 argument 60 degrees, so modulus of 32 and the angle 60 degrees. Okay, part 2 of example 9, we're given 3.2 argument 18 degrees multiplied by 5 argument negative 34 degrees, or divided by 6 argument 75 degrees. So part 2, what we do here is first of all multiply the moduli on the top and divide by the modulus on the bottom. So we get 3.2 multiplied by 5 divided by 6, the r. And for the arguments here we've got the plus 18 degrees plus a negative 34 degrees, and that's then take away the denominator, the 75 degrees. Very careful with your directed signs here. So 18 degrees plus the negative 34 and then minus the 75 degrees. Be very careful there with your directed numbers. Evaluating that sum we get 2.667 for the modulus and an argument of negative 91 degrees. Part 3, we're given 5 argument pi upon 4 divided by 2 argument pi upon 8. Obviously those are angles in radians here. So for part 3, we end up with 5 divided by 2 for the modulus, and we end up with the arguments of pi upon 4 subtract pi upon 8. Evaluating this, we get 2.5 for the modulus and an argument of pi upon 8. Just be careful there with your use of fractions. Pi upon 4 is 45 degrees, so pi upon 8 is 22.5 degrees. So questions 34 to 36, we're asked to undertake the calculation stated in polar form. So for question 34, part A, we've got 2 argument 40 degrees multiplied by 5 argument 20 degrees. So again, multiply the moduli and add the arguments. In part B, we've got 2.6 argument 72 degrees multiplied by 4.3 argument 45 degrees, and the same process required there. Answers are given in the square brackets. Question 35, we have a complex number in polar form divided by another complex number in polar form. And in part B, we have a complex number in polar form multiplied by another complex number in polar form divided by another complex number in polar form. Just be careful of your signs in this particular case, as it's a negative 15 on the bottom line. Answers again shown in the square brackets. In question 36, similar again, we've got 2 complex numbers multiplied together on the top in polar form divided by a complex number on the bottom in polar form. Answers again in the square brackets. Be careful with part B of question 36. We are given 3 complex numbers in polar form and asked to add and subtract them. We cannot add and subtract in polar form, so implicitly this question wants us to work out each of these complex numbers in Cartesian form, add the real, add the imaginary parts and simplify, and then convert back to polar form to get the answer shown for B in the square brackets. Question 37, we're asked to solve the complex equations given. So on the left hand side we have 12 argument pi upon 2, angle in radians of course, multiplied by 3 argument 3 pi upon 4. That's all divided by the complex number 2 argument negative pi upon 3. We've got to equate that to the x plus jy format. So in this particular question, what we will need to do is work the sum in polar form, which is quite easy to do, multiplication division, and then convert that to Cartesian form, and then we can equate the real numbers on the left hand side with the x and the imaginary numbers on the left hand side with the y to solve the equation. In part B here, be very careful. They've given us 3 complex numbers and they're added or subtracted together. Now be very careful, you cannot add or subtract in polar form. So the first thing you need to do with part B is to convert it into Cartesian form, then do the add and subtract, and then convert back into polar form, because the answer needs to be expressed in polar form. Answers are shown again in the square brackets. Question 38, we're given 3 vectors represented as P in polar form, Q in polar form, and R in polar form. We're asked to determine in polar form the following. Part A, P plus Q plus R. So be very careful that straight away you put the polar form of the complex number into Cartesian form so that we can add these P, Q and R together, and you need to convert back into polar form to get the final answer. The same for part B, we've got P minus Q minus R. Again, put P, Q and R into Cartesian form and do the subtractions and then convert back into polar form. Answers shown in the square bracket. For reference, here's the solution to question 37 part A. We were given 12 argument pi upon 2 multiplied by 3 argument 3 pi upon 4, all divided by 2 argument minus pi upon 3. We have to work out the left hand side and equate it to the right in the Cartesian form x plus jy. So given the information in the question, I get 12 argument 1.5708, I'm using the decimal fractions here, multiplied by 3 argument 2.3562, and that's all divided by 2 argument negative 1.0472, equated to x plus jy. So in polar form, that will be modulus of 12 multiplied by 3 divided by 2. And in terms of the argument, we get the 1.5708 plus the 2.3562. And be careful of the double negatives here. We've got the negative 1.0472, but it's being subtracted in this particular case. So that gave us 18 argument 4.9742. We've got to equate that to the Cartesian form x plus jy. So we need to convert the left-hand side now into Cartesian form. So 18 argument 4.7942 can be written as 18 multiplied by the cos of 4.9742 added to j times the r18 multiplied by the sine of 4.9742. Evaluating that, we end up with 4.6589 minus the j 17.386. That's equal to the x plus jy. We now simply equate the real term on the left hand side, that's the 4.6589, with the x on the right hand side. We equate the imaginary term, so that's negative 17.386 on the left hand side with the y on the right hand side. And that gives us our solutions of x is equal to 4.6589 or y is equal to negative 17.386. The bibliography used to generate this presentation, some excellent textbooks I strongly encourage you to refer to for further information related to complex numbers. I hope this has been of interest to you, and thank you for viewing.